I had that like illustration-y thing going on up here, and I was having, I think, water drain into or pour out of a cone. I think it was drain into a cone. I'm seeing if I have one that can show out of a cone, just because that's kind of interesting too, but I don't think so. Conical tank, any other tanks? There's a ladder, there's a paint, sand pile, that's probably making it bigger, snowball. You want to see paint? Okay, we'll get the paint one up. I'll also get the conical tank one up. And maybe the sand pile one? A paint utility on a computer lets the user draw figures from a palette of choices. The basic operation is to click the mouse, hold the button depressed, and drag to create the shape chosen. So you're clicking and dragging. Oh, it's like in the paint program, and not actually paint. Like how in paint, I don't know, if they don't even use paint anymore. That was the old school. Yeah, that's what I used when computers were new. What?
That's what you should do when you're super bored.
So you're dragging it.
Oh,
man, Minesweeper is good.
Minesweeper was, yeah, that was pretty
But I
awesome.
don't think it's like. That was pretty awful.
Pretty awesome. No, I thought it was pretty
It is
awesome.
awful.
It was like one of the first games that was on. I think it was the first game on the computer.
Or when the computers got hit, you need to find them.
I had this old video game. It was called Commander Keen. It was a good one. It was on like one of those 5.5 floppies. And put it in. Took it down. Yeah, this one's not very fun. Anyway, let's go back to the conical tank. But we tried it, Denise. We tried it.
What about the sand one?
The sand pile one too. We could try that. This one actually came from an AP problem. It was a gravel processing plant, and so like, have you guys ever watched the Gold Rush? What's it called? It's on like the History Channel or something. The Gold Rushers, and they all try to like find more gold. And
The Alaskan gold.
that's what I was. And they have to process all the sands. They have this huge little like conveyor belts, and then they like have to load it, and then it separates on there and it pours.
So it's like.
This is kind of what's going on. Yeah, it's pouring. It just looks like it's going down. Anyway, so it's coming up on the conveyor belt and it's going down. They had something like this on an AP, and it was called a gravel processing plant. So it was the idea of a conveyor belt and a gravel. But especially anyone who English was not their first language, they were like, "What on earth is this problem all about? This gravel processing plant?" Even American kids are like, "What is that?"
Yeah.
So that's why they have this one, because it's like growing and building, and the volume of the sand is building, and the height is building. Anyway.
Yeah, but I don't think that's the shape of sand.
Okay, they tried. E for effort. They tried. Okay, let's go back to this one. Kiddos, in this one, fluid is being pumped into the tank. That's what the little blue line is for, like a hose. They probably should have shown the hose, and that's like pouring out. It's flowing. Okay, what I asked you on Friday is, are all the different dimensions changing at the same rate? To illustrate that, I want you to think about like a funnel. You guys ever seen a funnel? You've had this funnel, right?
Yeah.
So a funnel, and it has like a little hollow tube at the end with a little like nozzle. Anyway, when a funnel is being used, water is draining out of it, right?
Yeah.
Okay. So if you're thinking about a funnel, my question to you is if you're pouring water in, let's say the funnel gets like backed up, and so it's up to here and it's just like pouring down. Does the height of the water look to be going the same at the very beginning in this full funnel or at the very end? Does it look to be going faster at the beginning, the height changing, or at the end? Why?
It has less width.
It has less width,
Oh, probably 'cause
so it's
changing
covering
less.
smaller, less volume that it has to cover. Have you guys ever seen it where it's like, oh, it's taking forever, and all of a sudden it's like, zoom, it's just like gone at the very narrow part of the funnel?
But it doesn't change at all, it's just.
The volume is still pouring out the same rate because the size of the hole at the bottom is still the same. So the volume is going out the exact same at the beginning and the middle at the end.
Just doesn't.
But is the height changing the same? No, because the surface area it needs to cover, or you could almost say the volume if you make it like three-dimensional, what it has to cover as it goes down, it takes longer at the beginning, but then as the surface area gets smaller, there's less room, there's less space that it has to cover, so the height actually is increasing or going faster as it drains. Does that make sense?
It's
So
like
you
you
can-
finish the bottom of the ice cream faster than the top. It's
Something like that.
Yes, Sarah.
But you guys at least kind of understand what I'm saying. That's like a funnel, or even like a soda bottle, or something like where you're pouring when the dimension of the bottom, like when you're turning it upside down, when the dimension of the top is bigger than the dimension at the bottom, the height is going to be changing faster when it drains out at the bottom. That's math, because it's like, oh, well, there's less stuff for it to worry about. And that's why it's like, and then all of a sudden it just like goes out. Or like an hourglass, if you like try to turn one of those hourglass sand timers, right? It's just like, oh, it's going, it's going to take forever, like if you're playing Taboo or something where you have the timer and you have to wait. And all of a sudden it's like, oh, the time's gone, because at the bottom it just goes faster. So that's kind of a good visual for related rates, how something could be constantly changing. The whole is staying the exact same, but based on the dimensions, the height could be changing very differently than like the volume, for instance. And that's what's kind of going on in this problem that we talked about on Friday. Because in this problem, you have a conical tank and the water is draining out. And if you guys think about it, this is full, so this hole isn't changing. The speed at which the water is pouring out isn't changing. But as the water level drops, the height is going to be decreasing faster because the surface area is getting smaller of the top of the water. So it's going to look like it's draining faster because it is. The volume isn't draining faster, but the height is changing or decreasing faster. So the way that we can relate all of this together and think about how the rates correspond with each other, even though they're not equal necessarily, they are related, and that relationship comes from what we wrote down on Friday, which was the volume of the cone is 1/3 pi r squared h. And on Friday I was saying like, hey, do we love writing paragraphs of problems in our homework when we have to write the directions in the problem? No one likes writing paragraphs of directions, right? So really we're going to be super lazy by learning how to read the paragraph and translate it into the map. What's easier? All of this or this? Yeah, it's easier to translate, right? So if we can put this in math speak, if we can put this in calculus notation, then it'll just make everything way easier for us. So why did I write dH? Let me zoom in a little bit. Why did I write dH dt equals negative 0.2 feet per minute?
The water level changing the height.
Rate of the height. The rate of the height. That means height prime. But if you look at the units, height is going to be the feet. What's the x? Minutes, which is time. Good. So I'm not just going to do like dy dx. I'm going to do dh because it's height over dt because it's time. So my variables change, but it's still the same idea. It's still a derivative of h with respect to t. So if you want to, you could also write technically h prime of t. It just doesn't help as much with thinking implicit differentiation if you write h prime. dh dt kind of helps a little bit more. How did I get dr dt equals negative 0.1 feet per minute?
Because the radius is changing rate.
Good, the radius is rate. So it's not r equals, it's r prime equals, which you could write, but another way of writing that is dr dt, which helps us with implicit again. Negative 0.1. Now question, thinking about the situation, why is it a negative rate?
Because the volume is decreasing.
Decreasing. Yeah, decreasing. As my water drains, the radius of the surface area of the water, or the surface of the water, the radius is changing and the height is changing in a decreasing manner. If it was increasing, if it was filling up, those would both be positive. Where did I get dv dt from?
Well,
What is? That's the question. That's the unknown. That's what I'm supposed to find. So what is the rate of the volume when the radius r equals 1 and height equals 2? It says, does the rate of the change of the volume depend on the values of r and h? The answer would just be yes. And why? Well, because you need to relate everything with the volume of a cone formula. Because dv dt, if we know what dr and dh dt are, dv dt might change accordingly. But the problem is, all of these are rates. All of these are derivatives. So how am I going to take this formula and use it? Derive it. So cool kids, let's take a derivative, huh? What is the derivative of v when I take it? 1, because it's just like y, it's just like x. 1, but I need dv dt. Just implicit differentiation. It's like 1 dy dx if it was a y, but this is volume instead, so y dv dt. equals. Why did I do a box and a triangle around the rest?
Product,
Product, because there's a times. Now hold on. Why did I group 1/3 with pi with r squared?
That's 1/3.
1/3 and pi are both constant, so it's like the coefficient that I can just tie with one of them.
Yeah, 1/3 pi
Well,
r squared.
1/3 and pi are just coefficients, so I kept on expanding until I got to a variable. So 1/3 pi r squared, there's one variable, and the variable needs to be split from the other variable. Yeah. So if I do second d first, that's going to be h times, bring down the 2, good, so 2/3. The pi just chills, he's a constant. It's going to be r to the 1. Now hold on, who did I just take the derivative of?
Just multiply by the first.
The r's. So what do I need times u? I need dr dt.
Wait, is that because you derived?
Because I derived the 1 with an r.
Okay, so like an R is like a U.
Yeah.
So,
Or like a y. So I needed
Like
the
a-
dy dx.
So also same E.
Uh-huh. So when I go to do the next one and I do first d second, I'll keep the 1/3 pi r squared, but now I'm taking the derivative of the h expression. So what's the derivative of h going to be? 1 dh dt. You're right, you don't have to write the 1, but I'm just saying I am taking the derivative of h, it's 1. But I need the dh dt. If you want to think about it,
Oh, then you can
1 times b prime equals h times 2/3 pi r times r prime plus 1/3 pi r squared times 1 h prime.
If we had an x, it would just be one.
Yeah, well, since we're now doing it based on time, if we had a t, it would be 1. And x would actually be a dx dt now because it doesn't match.
So anything other than the denominator is going to be the dy or whatever?
So like before, remember we had f of x, y equals f of x,
Yeah.
and we were taking d dx. So d dx of y was dy dx. d dx of x, was dx dx, which just cancels. Yeah, so you can think any variable gets it, just if it matches, it cancels out to 1. Does that make sense? We want to solve for dv dt, right? Do we have anything we can plug in? R is 1, H is 2. Now question, is R always 1 and H always 2? No. So this is talking about 1 instant at time. 1 instant of time, or 1 instant in a situation. Which is why I couldn't plug these in earlier. So if I plug them in at the beginning, I'm saying it's constantly true. It's always true. If it was always true, I could plug it in here and find V. Problem is, I needed to wait until I took the derivative and then say, okay, what instant are we talking about? Oh, this one. When R is 1 and H is 2. Okay, let's plug it all in. And these are constants, so I'm going to plug them in as well, because it's always true. So I have, what, 2/3 pi r h, dr dt, which would be negative, 0.1 feet per minute, plus, now I'm not doing dimensional analysis so good, I'm not plugging in all of my, 1 squared times 1 dh dt would be negative 0.2. Could I plug in all my units? And the answer is yes. We'll think about units in just a second. So far we're just plugging in all of our knowns. And the nice thing is, look at this, guys. Isn't this something that we just need to simplify and solve? Because I have every single unknown in here. Now, if for any reason I was missing 2 things, not just dv dt, but if I was missing something else, there was some sort of clue I missed. And sometimes it's hidden, and sometimes it's based on geometry and something that we haven't thought about in a long time. But this time, all we need to do is simplify. So, let's see, I see 4/3 pi times negative 0.1. That'd be negative, 0.1 would be 1/10. So 4/3. 4/30 pi. Plus, and then I have 1/3 pi times 2/10. If I want to do common denominators, that I would just leave it as 2/10 and not 1/5. So that'd be 2/30. You guys can double check my mental math. I think I have negative 6/30, which would be negative 1/5 pi. You could also do decimals. I think you would have gotten negative 0.2 pi.
So the derivative of pi is
The derivative of pi would just be 0 because he's a number, which is why we just let him tag along because he's a coefficient like the 1/3. So wherever the 1/3 was put in, the pi was put in.
Okay, and then for R, I just.
The pi, we didn't need a d pi dt because the derivative of pi would have just been 0. So we didn't do a product rule here.
Okay.
They just were the coefficient, and we were just dealing with the r squared, which is why I just brought down the 2, and it joined the rest of the coefficient, and it was r to the 1 times r prime.
So it became 2 because.
The 2 came down. Sorry, that's a 1/3.
Oh, okay.
So 2 times 1/3 is 2/3.
Okay.
That makes sense.
Yeah, I thought it would be. I was like, why is it 6?
Oh, because, yeah, sorry. The 1 got covered up by my box on
That
Friday.
looks like
It's a 1/3. Sorry. I don't know if that helps though. Kiddos, there were units to begin with, there needs to be units to end with. If you think about it, I'm going to put the units in different color. What were the units of the -0.1 and -0.2? Okay, so we have feet per minute for both of these. But we also plugged in, didn't we plug in R's and H's? So R would have been feet, right? And then H would have been feet. Oh, hey, feet cubed per minute? Why does that make sense, looking at what we took a derivative of?
Because that's the rate of change of the volume.
It's the rate of change of the volume with respect to time. So volume's going to be measured in cubic units. So we are going to have feet cubed. If you ever don't keep the units all along the way, if you've done it correctly and you haven't had to change like feet to miles or something ridiculous like that to make everything correspond, or minutes to seconds or to hours, you should be able to look at your differential, your derivative notation, and say, okay, I need dV, units for volume, feet cubed over units of time, minutes in this problem. So you could go back and then actually look at each of your units, and usually that works. Every now and then it's a little funny whenever we're doing like the angle increasing, decreasing. This is the one time it doesn't work super well. But with volume and time, we need feet cubed per minute. But that's exactly what would come out of up here as well. And if you're wondering, in this one, the h totally went away, but we have r squared, so we would have feet squared, which would still get us feet cubed per minute. Combine them, and then we got it. Does that make sense? I want to get at least one more practice problem, maybe 2 done. So what did we do? Someone real quick, in your own words. What did we do to solve this problem? We're done. That's it. Tyler.
Yeah, we just took the derivative of the volume formula and plugged in. Pretty much it.
But what needed to happen before we were taking the derivative of the volume formula?
Oh, we need to get all of those.
Good, the givens and the finds and proper notation, because didn't the proper notation tell you this better show up somewhere, and this better show up somewhere, and this better show up somewhere? And then where did this come from? It wasn't given here.
Snow.
We had to review some geometry. Alright. So, let me give you a second. You write down what you need, but hopefully you saw me do each of these things in that problem. And you guys did them with me. It wasn't like me doing them alone. But related rates. This is not going to be a forever card, just because it's more of an understanding that when they say rate, you know derivative. And we've already written that down. Instantaneous rate is a derivative. Implicit differentiation, it's more of a process, taking ddt of both sides, like ddx, and plugging in, so I'm not making it a forever card. It's more of an understanding. Sometimes you have to come up with the formula yourself, or you have to use like a geometry formula. Take a derivative of it because there's movement and change, and so you need to look at the derivatives, the rates. You need to learn how to translate with calculus terms too, not just the old-fashioned product sum is
If you were to,
square variation.
if you're to accidentally do related rates on a
Motion problem.
problem with a constant rate,
You would have like a DRDT that you would need to be like, I don't have this to plug in. Reread the problem and say, oh, the radius isn't changing. That's 0. So it's like an extra level. If the radius is staying the same, then the dr dt would be 0. Because it's, and you're like, oh, it's constant. Oh, this should have been. So you could go back to your equation and then plug in a 0. But you're going to have to relook at the problem again. Which that's going to be true at any point if you've already done your givens and you found the derivative and you're like, wait, I'm missing something. We're going to have to go back and reevaluate. What did we miss? At some point, we're all going to miss something. That's okay. It's not a bad thing. It's a learning opportunity. You guys will be skipping the line. Sorry, I didn't say that, but if I were you, I would highlight this. Just don't mark it a forever card, because basically it's word problem stuff. Read it, identify it. The extra step is figure out an equation that you can use for it from your past experience, and then plug in what you know to find what hopefully you don't. Yeah.
If it's a problem that doesn't relate volume,
Right.
Will they give us an equation, or
On the AP, they have been nice with abstract or really specific formulas to give them to, but there are ones like volume of a cube or a rectangular solid or area of the circle or area of circumference of a circle, volume of a sphere. There's some that you better know. But then there's like area of an equilateral triangle, but they probably wouldn't make you come up with the formula. They have given like in parentheses at the end, like P.S. there's this formula that you should know and probably use. But like they won't give you Pythagorean theorem if that makes sense.
Yeah, but look kind of let me see. It's more.
Yeah. So with respect to time, first of all, so we're doing DDT. Almost always at both sides. Just a heads up, there are going to be multiple rates of change. And sometimes even multiple formulas. And maybe we're taking DDT with multiple formulas and trying to put them together to do some substitution and things like that. Sometimes we'll have like systems of equations and we're taking derivatives of them. Non-changing quantities, like if you visualize what's going on, which is always a good idea, and if something is not changing as it's moving, then the rate is just going to be 0. So maybe you have like a dr dt or a dx dt or a dy dt, and as you think about it, you're like, wait, that measurement isn't changing. Well then, I should have caught this earlier, it's constant, so it doesn't have a rate, I plug in 0 for that. Remember again, rate is referring to slope on a graph. That's referring to the derivative of if you have the rate of somebody, which you can have a rate of all sorts of different things, it means that you're looking at the derivative of that something, of that quantity, of that measurement. Did I show you guys the ladder example on Friday? With the chair and it like slammed down? So like in that example, the length of the ladder or the length of the chair, that wasn't changing. What was changing is how high and how far out it was. That's what was changing, but the length wasn't. So that would have been something where the ladder, if we had called that, or the chair, if we had called that like C, like the hypotenuse of a right triangle, then dc dt would have just been 0. Okay, are we almost there? A couple more seconds.
So for something that's constant, do you put in a 0 after the divide?
Yes. Because you're not putting in a 0 for what the measurement is, like what the r equals or the h equals. You need to put in a 0 for the dr dt or the dh dt. Okay. You guys don't necessarily need to write these down. I just want you to read them and see if it makes sense. Okay? So the velocity of a car after traveling for 1 hour is 50 miles per hour. If you call the position or the distance traveled x or s, it need to be dx dt or ds dt, which would be like x prime or s prime. But velocity is the rate of change of the position or the distance of the car, the distance being traveled. So we need x prime or we need s prime, which we do usually call it v, but just Technically, we've been doing this ever since we did motion. Water is being pumped into a swimming pool at a rate of 10 cubic meters per hour. Now, hold on, cubic meters, this should be a clue. Cubic meters, what's that measurement? Cubic. Volume. Oh, because water's three-dimensional, so three-dimensional is getting poured in, the volume is changing. Why is it a positive?
Because it's going in, not
It's
draining
being
out.
pumped in, and so the volume is increasing in the pool, right? If it was draining out, then it'd be negative, it'd be decreasing. Okay, a gear is revolving at a rate of 25 revolutions per minute. Revolutions? We're talking about revolutions, we're talking about angles. So this is going to be a d theta dt with the angle of revolution, but here's the weird thing, they don't want to leave it in revolutions. We don't measure thetas in revolution, we measure thetas in radians. And so we'd have to say each revolution has 2 pi radians. That's going to be like a dimensional analysis thing where we build a bridge to get rid of what we don't want. So we're going to multiply by 2 pi radians over 1 revolution, and then we get to cancel out revolutions and have d theta dt. Dun, dun, dun. Population of bacteria is increasing at a rate of 2,000, that's intense, 2,000 per hour. Well, you have to name the population something. So sometimes you don't even use like an actual mathematical variable or symbol or anything like that. It's just like whatever, just call it x, we don't know. So some population is growing, call it x, so dx dt. We call it p for population, call it dp dt, I don't care. But why is it positive? What if it was dying off? It's going to be negative. Alright. Sometimes the problems are as easy as this one. They give you an equation. What? Don't you have to work for it? They give you an equation and they give you some related rates clues. So what are we going to do if they give us an equation and then say, hey, I'll tell you one of them, can you go find the other one? Do we really have to work for this, or is it all just ridiculous? So this is a very atypical one. This is a very like basic, fundamental, beginning, simple one. Where it's like, hey, here's the equation. You don't even have to work for it. Here's the given. Wrote it out. Here's the find. So you guys understand why I'm going to start writing ddt up here as you guys finish writing the problem? There's not even a product rule. It's all like power rule, right? With implicit. So does that make sense? They give us a dx dt. Oh, they want rates. Okay, fine. Let's take the derivative. I knew it was ddt because of how they wrote or what they wrote the rate as. And I had to do implicit, so I have my x prime, y prime, x prime, y prime. Oh, what's my last step? We could do dy dt alone. Or just plug in and say we'll figure it out in a little bit because he's the only guy who's going to be left standing, right? So I could plug in 2 times x, 2 times 3, times negative 5, plus 2 times y, 2 times 1, dy dt, don't know him yet, equals 2 times negative 5, plus 4 dy dt, don't know him yet. So now I have numbers, which is considerably nicer because 2 times 3 is 6, times negative 5 is negative 30, 2 times negative 5 is negative 10. I could subtract the 4y t. Now that I just have numbers, I can just like combine my terms. I can add the 30. You guys look at my mental math, I think it's negative 10. There are no units because they didn't give me any, so alright, fine. According to a point or points that are related on this graph, you have a point that's moving on this graph, if dx dt is negative 5, the horizontal position is decreasing at a rate of 5, I don't know, units per minute, hour, second, then y is going to be decreasing by 10, or at a rate of negative 10. Sorry, decreasing at a rate of 10, which would be having a rate of negative. Don't say decreasing and negative at the same time. You'll get in trouble. but how bad was that one? Not bad, as long as you understand implicit, right? So the point isn't that the math is hard. The point is what happens when they give us words. It's okay. Now, the very first thing you should write down is the balloon problem. And balloon being inflated, or inflating a balloon. So in homework, just so that you can say it's the rocket problem, it's the plane and observer problem, it's the ladder falling problem, it's the tank being filled problem. Just identify it real quick. But then, you don't need to write anything else as far as the paragraph. We're trying to break it down into the given and the found. We're trying to break it down into how can we mathematically state what we know and what we need, and then let's figure out what other connections we need to make based on basically all of our previous training in math. Has anybody figured out something that we can write as a given?
DVT.
Good. Good. dVdt is 3 feet cubed per minute.
Find would be D. Well, D.
Yeah.
You're finding DD.
Yeah, that's okay. Because this D stands for differential, differentiate, right?
When
So this
R
is diameter.
or the
Such that
R is equal
R1 is my instant. That's like what I plug in after the derivative. Now the dilemma is, okay, that's great and all, but what do we need?
So you need the 4/3 pi r cubed formula.
Good. Tyler just reminded us of the volume formula for a sphere. So we need the V equals 4/3 pi r cubed. Kiddos. V. We want him. We need him. dVdt. We're going to plug in using, after we take a derivative, using that V. What's the dilemma, though, with
Well, you have
the
to.
other part?
It's
You
in
want-
diameter.
Oh,
Yeah,
it's not
should you-
diameter. Now we have two ways that we can go.
1/2 D times.
If R is half the circle, D is the whole thing, right? So what does D equal?
2R.
Okay. We have two options. One option is let's get rid of R right now.
Yeah.
And get D in there before taking a derivative. Or the other option is let's take a derivative and be like, uh-oh, I'm stuck, I don't know what to do, and then go look at the other formula for help. I'm going to go ahead and do the second one, just because not all of you would have noticed that R is not D, and that might be a dilemma. You would probably just have gone with it and be like, yeah, I have a formula, let's go, take dVdt. 4/3 is a constant, pi is a constant, I get 1 dVdt is equal to, bring down the 3, it cancels with the third, you just get 4 pi r squared dr dt. But as you go up here and say, let's plug in, are we solving for this guy?
No.
No. Well, you would have had to think about, well, diameter is 2 times radius. You would have had to go looking for another clue, something that we missed or didn't consider. Could we take the derivative of this and get d dt in terms of dr dt? Yes, and it would have been the exact same thing that would have happened if we had gotten rid of r at the beginning and gotten our d's before the derivative. So we can go both ways. We can derive first and then go looking, or we can go looking and then derive. So at the end of the day, if we want to plug in for dr dt, we would need to divide by 2. We would have dv dt is equal to 4 pi r squared times 1/2. Now do I have it all ready just to plug and chug? Alright kiddos, with that imaginary bell beep, this chapel thing. I'm going to go ahead and just plug and chug to finish this puppy off, but all we need to do is throw in that 3. 4 pi, throw in the 1 for r, solve for ddt. We just have to get it by itself. Does anybody know what the units would be as you leave?
For what?
No, not cubed. Volume was cubed, so this one,
Diameter would be feet.
Feet squared over
No,
minute.
2.
diameter is just measured in feet. So when you divide by, here we go, feet squared, because that would have been the radius, so you divide by that, you would just get feet. I think diameter must be feet, time must be minutes. Bye, cool kids. I'll see you later. Get started on this homework. It's a feast. Get into it, get stuck, come back tomorrow, we have more things. It just takes time to read, to analyze, and to solve. Welcome.